Okay, now we're going to we've been making sort of parallels between rotational motion and linear motion, and we've used that to describe sort of rotational kinematics, like how do I describe how many turns something has gone through using the same approach that we use for linear kinematics. Now, the really cool thing we're going to do is we're going to extend that to dynamics. That is, how do forces control how things move? And so we remember that we have, for linear dynamics, we were basically using Newton's second law. And there's a version of Newton's second law that we can apply to rotational dynamics. It's basically paralleling what we learned for linear dynamics in chapter 4. So remember that we have already described a tangential acceleration. That would be if I've got something that's rotating like I've illustrated here at some rotational velocity omega. If omega is increasing, then that means there is a rotational acceleration alpha, and that means that some point out here is going to be at each subsequent time step. So if I've drawn these lines at equal intervals in time, we can see that the object is moving around faster because the rotational speed is accelerating, it's speeding up. And so that means that there is a tangential linear acceleration. That means that there's a linear acceleration along the direction of motion as well as the centripetal acceleration towards the center. And of course, if there's an acceleration, there must be a force causing that acceleration. That's what we know from Newton's second law. And so that tangential acceleration is equal to whatever that tangential force is over m. Well, that force is the force that's causing this thing to rotate faster. That is the force that is giving a torque. And we remember that the relationship between the linear parameter and the angular parameter is that the linear parameter is just the angular parameter times r. And so if I substitute these two things together, I get that alpha equals F, that's the tangential force or the force that's causing a torque, divided by mr. Well, it would be nice if we had an expression for rotational motion that was along the same lines of Newton's second law, where we had force equals m times a, mass times acceleration, and we want to replace the force with the torque, and we want to replace the acceleration with the angular acceleration. Well, the relationship, of course, between the torque and the force is the torque is equal to r times that Ft. That means if I substitute Ft is torque over r into this equation, I get alpha equals Ft, equals the torque over mr squared. And rewriting that, that gives me torque equals mr squared times alpha. And that is parallel to what we had with Newton's second law. We have Newton's second law tells us F equals ma. Now we have, for rotation, torque equals mr squared times alpha, where alpha is the rotational version of acceleration, torque is the rotational version of force. So this quantity here, mr squared, must be the rotational version of mass. And that's what's called the moment of inertia. And so that is defined in the slide here that shows that for any kind of an object, here looks sort of like a painter's palette, we can add up the mass of each individual piece of that object times the square of the distance of that piece from a rotation axis. And if we add that all up, we get something called the moment of inertia. So the moment of inertia, we use capital letter I, is the sum of m sub I r sub I squared over all of the pieces of an object. So we're going to be working with simple objects where we can, like, say it's a point here, a point here, a point here, and we're going to add up the mass times the distance for those individual pieces. Or if we've got some complicated object like what is shown in the slide here, we're going to have already done this summation offline, so to speak. So you're not going to have to do it. That would involve calculus to actually be able to figure out what the exact moment of inertia is for some odd-shaped object. But it is always proportional to the mass of the object and the square of some length scale. So it's always got kilograms times meters squared. The kilograms is the total mass of the object. Meters is some measure of the distance of the object. And it depends. Like if we're taking this pencil, it could be the length of the pencil would be the natural length scale of this thing. But if I'm rotating it this way around its axis like that, then it wouldn't be the length of the pencil, it would be the thickness of the pencil instead. So it's some measure of the length scale relative to how that thing is rotating. But it's always going to be those two things, and then it's going to be times some number. And so we always are going to have a mass times a length scale squared. This is the moment of inertia. That's sort of like it plays the role that mass plays in linear dynamics for rotational dynamics. Mass is the resistance of something to moving. Remember Newton's second law, F equals ma. That rewritten says A equals F over m. The rate of change of the motion of an object, which is the acceleration, is inversely proportional to the mass. The bigger the mass, the harder it is for that thing to move around. Well, the moment of inertia just says the bigger the moment of inertia is, the harder it is for that thing to change its state of rotation. So we'll do some examples with that, but this synthesis slide here just summarizes what I've just been saying. In linear dynamics, we have F, M, and A, and Newton's second law. Now we just have the parallel of that for rotational dynamics. Instead of force, we have torque. Instead of linear acceleration, we have angular acceleration. Now instead of mass, we have this quantity called moment of inertia. For any particular object, for moment of inertia, if it's a simple object, we can calculate it. If it's a more complicated shaped object, we're just going to look it up in a book. But it is going to have the total mass of the object and some measure of the size of that object in there. So as an example from that, we see in the slides here for a rod, if it is rotating around the center of the rod, like this, the moment of inertia is 1/12 times the mass times this length squared. Where did that 1/12 come from? It came from going through and calculating what the moment of inertia of each individual piece of that thing would be using the center of the rod as the reference point. We can, you don't need to worry about calculating that 1/12. That will be given to you, or we can look it up. And if we were doing a calculus course, we would learn how to calculate that value of 1/12. If instead of rotating around the center of the object, I'm rotating around the end of the object like this, same object, just a different point of rotation, then the moment of inertia is not 1/12 ml squared, it's 1/3 ml squared. It makes sense that that coefficient is bigger if I'm rotating around the end, because now I've got stuff that can be very, very far away from the axis. And since the moment of inertia depends on the square of that distance, it's going to be much bigger in that case than it was when the axis was in the center of the object. So in general, we're going to say that I is some factor k times m times some length scale L squared for the object, and K, I keep having random things pop up on my screen. K depends on the object, and you don't have to calculate K, but you should have some intuition for the different, whether K is bigger or smaller for different types of objects. Yeah. If we were in class, we would do a fun demonstration where I roll a cylinder or a hoop down a ramp, and you would see that they roll differently. I'll see if I can find a video to link for you guys for that. But here in this table 7.1, you can see that if I have a solid cylinder, the moment of inertia is 1/2 mr squared. But if I have a hollow cylinder, it's mr squared without the half. In other words, it's a bigger moment of inertia. Why? Because the mass, on average, is farther away from the axis. All the mass is as far away from the axis as it can possibly be. Whereas for the filled cylinder, some of the mass is actually close to the axis. So its R is not the full radius of the cylinder, but a smaller value. And so that contributes to lowering the overall moment of inertia. In the hollow cylinder, in the bottom row there, all of the mass is as far away from the axis as it can possibly be. So each individual piece of mass is a distance r from that rotational point. Whereas for the solid cylinder, some of it is closer. So the r value for that is smaller. So while I don't expect you to memorize those coefficients k for these different objects, you should know that the uh, greater the distance on average of stuff from the axis, then the larger will be the moment of inertia. So a hollow object of the same mass is going to have a higher moment of inertia than a solid object of that same mass. And that we again see here, the solid sphere, k is 2/5. For a spherical shell, it's 2/3, that value of k. This is again assuming that the masses are the same. Of course, if the mass is bigger for one or the other, the moment of inertia increases proportionately. Let's go ahead and do an example. Problem. So in the book here, they've worked out an example with the balancing pole for a tightrope walker. Let's do one from the book. Let's do chapter 7, number 42. And in this, there is a merry-go-round that is a uniform circular disc that has a radius, has a diameter of 1.8 meters, so has a radius of 0.9 meters. And it's a uniform, we can model it as a uniform disc. It rotates around this central axis, so that's our axis location. And the question is, let's see, it has a mass of 88 kilograms. So this is like a playground merry-go-round, not like an amusement park carousel. And the question is, how many children stand at the edge to double the moment of inertia of this merry-go-round? where the mass of each child is assumed to be 22 kilograms. Well, let's calculate the moment of inertia of the merry-go-round. Call that I sub m. It's a disk, and we're just going to look up what the value of k is for a disk rotating around the center. We don't need to memorize it. And it is 1/2 mr squared. Okay, so k for a disk rotating around the center is 1/2. The moment of inertia of each child is just the mass of the child times its distance from the central axis, so mr squared. I put a little subscript m for merry-go-round under the mass of the merry-go-round up there, and m sub c for mass of the child. So the mass of the merry-go-round to begin with is 1/2 times 88 times 0.9 squared. Now let's figure out what that numerical value is. 0.5 times 88 times 0.9 squared is 35.6 kilograms meters squared. That's the units for moment of inertia. And I want to double it. Well, the mass of one child is just 22 times 0.9 squared, and that is 17.8 kilograms meters squared. I need to double the total. To double the moment of inertia, I need to get an additional 35.6. That's my dogs barking, if you can hear them. Here's Olivia. She keeps me company. Olivia, 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 say hi here. So Olivia keeps me company while I'm making videos for you guys. So I need an additional 35.6 kilogram meters squared from the kids. Well, 17.8 plus 17.8 magically turns out to be 35.6. What a coincidence that they wrote the problem that way. So 2 times 17.8 is 34 plus 1.6, so it's 35.6. So 2 kids doubles the moment of inertia of the system. So that's just a simple example of calculating moment of inertia. In the next section, which will be in the next video, we'll take a look at actually using the moment of inertia to calculate the rotational dynamics of an object.